Hello, and welcome back to another Math 104 lecture. So, where we left off last time was we were talking about interest, right? And we were discussing simple interest, compound interest, and then I brought up the idea of continuous compound interest. So, when we were talking about compound interest, we saw that compound interest is dependent on a couple of factors, right? It was dependent on your principal amount or the initial amount that you were putting in. It was also dependent on the amount of years that it was compounding. So far that's pretty similar to simple interest. But the big change here is also how many times it's compounding per year. Right? In simple interest, that wasn't a factor because it only happens once, every year, and the interest is only on the amount that you put in. Compound interest is where you gain interest on your interest. You gain interest on the amount that you gain per year on top of the amount that you first started with, which is why it matters how often you're compounding. And what we proved last time we looked at this was even if you keep everything the same, so even if you keep the number of years the same, the interest rate the same, and your principal amount the same, as you compound more and more frequently per year, you will gain a larger amount of money. And so the question that I posed to you is, okay, so what happens if we try to compound as quickly as possible? So instead of compounding twice a year, 3 times a year, or even daily, what happens if we do it twice a day, 3 times a day, so far and so forth, for the entire year? So as much as you can. And that leads us to a really interesting concept. And the way I'm going to present this is I'm not going to show you the derivation because the derivation of it it matters greatly, but also I feel like it's a bit outside the scope of this class. You have to have a bit of like either pre-calc or calculus knowledge to really understand what's going on here. So instead, how I'm just going to present it as I'm going to present the number, and I'm going to give you guys the formula, and we'll talk a little bit more about it. So the number that falls out here when you do, try to compound more and more and more as often as you can is Euler's number, and I'm going to spell it here, E-U-L-E-R, Euler. He was a Swiss mathematician, and he was one of the greatest mathematicians to ever exist. Actually, he has not one, but 2 numbers named after him, but the other number we don't really touch in this class. So Euler's number is just represented as E. And also for the record, it is pronounced Euler, not Euler, like E-W-L-E-R, again, Swiss, right? So if you pronounce it Euler, F, just immediate F in my class, it's Euler. Pronounce it Euler. Again, pronounced like that, okay? Anyway, so Euler's number is the following. E is equal to 2.7182818, and it goes on forever and ever and ever. This is an example of an irrational number. We've talked about rational and irrational numbers going way, way back at the beginning of this class, where rational numbers essentially have an end, and they have an end because you can represent them in a fraction, right? An irrational number is something that you can't represent as a fraction, and it is just going on forever. We cannot predict necessarily what the next number is unless we actually do the computation to figure out what that next number is. So in general, we do round this, and we round it to approximately the 4th digit, so it's about 2.718, and that's the number that we generally use for Euler's number. So where does Euler's number fit in when we're talking about compound interest? Well, again, if we're talking about continuous compound interest, then that's when we use Euler's number. That's when we use E. And the interest formula then becomes A is equal to P e to the RT, where P is still your principal amount, that's still the initial, A is still your total after everything is said and done, R is still your interest rate, and T is the amount of time the amount of time in years that you are compounding. So let's look at a quick example using the same values that we used for all the other interest values that we did before. So let's say again, we want to figure out what the value is going to be if it's continuously compounded, where the principal is $100 or 100, however you want to think about it. The interest rate is 4%, and the time that it's compounding is for 6 years. So how you would set this up is you're just plugging in, right? So A is equal to P e to the RT. So you have 100 times e to the RT. So in this case, it'd be 0.04 because, again, that's your interest rate times 6. And when we simplify this, we get 100. That's not 100. 100 e to the 0.24. And when you plug this into your calculator, because there's no way I expect you to do e to the 0.24 in your head, you would absolutely use a calculator if you've gotten this far. And what you get is a is equal to 127.2, and it actually goes on forever, but I'm rounding to the 100th here because if we're talking about money, I'm just rounding to the nearest cent. Okay, so you may not remember this immediately, but 127.12 is the exact answer that we got when we were compounding daily. So when we were compounding daily, that's when we plugged in the same values for P, for R, and for T. The only difference is that, we were, our formula was a little bit different, and we saw that we were, dividing our interest rate by 365, and 365 was also in our exponent. If you don't remember what I'm talking about, that's in literally the last lecture right at the end of the lecture. So please, just go examine that and it'll make more sense. But in any event, we got this same thing, a is equal to 127.12. And you might ask me, okay, so does that mean that compounding daily is the same thing as compounding continuously? And the answer is no. The reason that we got 127.12 for both answers is simply because the values that we're plugging in are so small that the answers match when you round them to the 100th. If you were talking about to the 1,000th place, to the 10,000th place, and so on and so forth, so if we're talking about, these decimals that continue after 0.12, then those numbers actually start to change. And what you'll see is that this one right here will always give you the greatest response. It'll always give you the greatest value or the largest outcome. It just so happens that in this case, they match because the values are so small that, the decimal places aren't going to have a lot of flexibility until later down the line. But the point is that either way, notice how A is equal to P times E to the RT, this formula that we have for continuous compound interest. Notice how this is still more, like substantially more, than when we, compounded semi-annually or annually, right? If you were only compounding once a year, twice a year, 3 times a year, so on and so forth, if your number is very, very small for the amount of times that you're compounding per year, then the difference is going to become really apparent. If you're compounding a lot, like, more and more often over the course of the year, then you are approaching this equation. So as you compound more and more often over the course of a year, you are approaching continuous compound interest. And approaching continuous compound interest, again, I brought up the concept of a limit, where, limits we're talking about as you get larger and larger and larger, or smaller and smaller and smaller, either to infinity or to 0. That's where we get E from. And again, I'm not really going to go into depth as far as the derivation of this number. Just understand that, it has to do with limits. And if you want to talk about it with me in private, if you are interested, feel free to reach out to me and we'll go over it a little more in detail. It is also in your textbook, but without a background in pre-calc, you're not going to make too much sense of it from your textbook. Okay. But in any event, that's all you do. You're just plugging in. E is not a variable. E is a number. Okay, so try not to get confused here. You're not finding a value for E. E is a number, and again, that is approximately 2.718. But when you're plugging in, because you'd be plugging into your calculator, just there is an E button on your calculator, and it automatically, raises to an exponent. So you're just going to be clicking that button on your calculator, or, there's resources online that do the exact same thing. Okay, so you're just plugging in for your principal amount, which is here, your rate, and your time. And once you do that, the rest just falls out. Okay, so we're going to finish up this chapter, and there's one last piece of this chapter that we need to discuss. So what we have to talk about is the natural exponential function. So remember, this entire chapter is all about exponential functions, and that's in the form of f of x is equal to c times a to the x, right? And then I brought up that, okay, the basic exponential function is where c is 1, and then you just have a to the x. Well, the natural exponential function is where you have f of x is equal to e to the x. And now I'm going to stop here, and I'm actually going to go back to something that we talked about at the beginning of last lecture, because I realized that I didn't really specify this, and I want to make sure that I go over it before I continue. So if you guys remember, oh, I'm running out of room here. Sorry about that. Let me zoom up and go way over here. Okay, so if you guys remember, I had, and I'm just going to freehand this because, you know, it's just going to make more sense here. I had drawn earlier at the beginning of the last lecture the following functions. I had in red, f of x is equal to 1/2 to the x, and then g of x is equal to 2 to the x. And what we saw is the following. We saw how g of x kind of looked something like this. And we saw how f of x did something like this, right? And we know that these are opposite functions, and the reason that we know that is because it reflects over the y-axis, right? But there was one detail in particular that I didn't go over, and that was if you're talking about the rules or the facts of these exponential functions, the one thing that I didn't go over is how specifically one graph of an exponential function might lie above or below another. So this was the fifth fact, and I'm just going to write it out one more time. So the fifth fact was, and I will put a 5 here, if 0 is less than a is less than b. So all this saying is that you have two numbers that are both positive, where one is just larger than the other. And g of x is defined by the larger number, so b to the x, still an exponential function, it's just the larger one. And then f of x, also an exponential function, represented by a to the x, where a is the smaller number, a is less than b. So f of x will lie below g of x from 0 to infinity. So we're talking about our domain here from 0 to infinity. And lie above, and I'm running out of room one more time here, sorry guys, lie above g of x from negative infinity to 0. Okay, so let's examine the graph here, and then we'll go back to the natural exponential function, and it'll make a little bit more sense. So again, g of x is the green line, right? So I have g of x right here. And notice that g of x, well, 2 is bigger than 1, right? We can agree that if we're talking about 0 is less than a is less than b, in this case, our two bases are 1/2 and 2, right? So we have 0 is less than 1/2 is less than 2. So what should happen? Okay, it says that the graph of f of x, which has the smaller base, should lie below g of x from 0 to infinity. So 0 to infinity is from right here forever, right? So it starts at 0 and then we go on to infinity. This is talking about the, we're talking about our x inputs, our domain here. So if we're talking about the graph lying below, that literally means below. Like we're talking about, from bottom to top. So notice how my red line is lying underneath the green the green graph here. So f of x is lying below g of x because the base is smaller. And that is always going to be the case whenever you're comparing two exponential functions where one has a larger base than the other. If we're talking about from 0 to infinity, the one with the smaller base will lie underneath the one with the larger base. And now, if we're talking about the opposite, so we're talking about, and again, I'll just notate this is from 0 to infinity. And if we're talking about the other piece of it, so, oh God. That was miserable. There we go. That's better. So if we're talking about here from negative infinity to 0, once again, now notice how the red line or the red graph is above the green graph. And this is, again, we're talking about from negative infinity to 0. So all of the x inputs that are negative up until you hit 0, we're always going to have your function with the smaller base lying above the function with the larger base. And again, the reason that this is true is because as your exponent gets larger and larger and larger for something like this, notice how this is a decreasing function. 1/2 to the x is a decreasing function. It is going down. We're starting from infinity, a range of infinity, and then it's going down closer and closer and closer to 0. Whereas with something with a base that's larger than 1, it's going to be the opposite, right? We see how it's an increasing function. We're starting from 0, and I'm just going to put this in green here. We're starting from 0, and we're going upwards towards infinity. So notice that, again, you're going to have these kind of weird weird exchanges between the two, where on one half of the graph, one is going to lie above the other, and then on the other half of the graph, they're going to flip. And that flipping point is always at the point 0, 1, always right there, because they both go through that point, and that's the point where they switch as far as which one is lying above the other. So now, with that being said, let's discuss the natural exponential function. So a natural exponential function, again, is where your base is e. So that means your base is approximately 2.718. And what do we know about this number as far as comparing it to some other numbers? Well, comparing it, we know that it's going to be bigger than 2, and it's going to be less than 3, right? So if f of x is this number to the x, so again, e to the x, we know then I'm just going to call this over here h of x. It's 3 to the x, and over here I'm going to call this g of x is 2 to the x. What we can expect to happen is we can expect it to follow the exact same rule that we just talked about here, where it's going to lie above certain exponential functions on certain parts of the graph and lie below those same functions on the other half of the graph. So let's go ahead and plot this really quickly. So just again, this is going to be a rough sketch, but that's okay. So rough sketch of here, right? We know it's always going to go through the point 0, 1, regardless of what your base is. So all three of these functions are going to go through that point. Okay, so let's just quickly say, let's say, for example, this is e to the x, right? Okay, so this is my function f of x, which is represented by e to the x. Okay, so because we know that this is larger, our base here is larger than 2, what we can say is that we know that it's going to lie above 2 to the x from 0 to infinity and lie below 2 to the x from negative infinity to 0. So we know 2 to the x is going to look something like this. And you know what? Let's just try that one more time, just to really hammer in how it should look. There we go. That's a little bit better. And then g of x, well, now we know that, again, this number is less than 3. So when we're talking about the exponential functions where those numbers are the bases, then e to the x should lie above h of x. So this piece should lie above h of x from negative infinity to 0. So let's just plot this right here. So this is going to be my green line. And it's going to lie below h of x from 0 to infinity. Okay, so all I'm trying to represent to you here is that the facts that we talked about earlier are still going to apply, even though your base is e. Even though your base, it looks like it's just a letter, but that letter is indicative of a number. And so, because it's approximately 2.718, it's going to be greater than 2, it's going to be less than 3. So when you set these all up as exponential functions, the facts are still going to hold out here. Okay, so the last thing that we need to discuss now that we figured out what e is, now that we talked about exponential functions, the last piece is exponential growth and decay functions. Okay, so these are just formulas that, unfortunately, there's no better way to remember other than just memorizing them. So bear with me here. Growth is represented as the following. It is a of t is equal to a sub 0 e to the kt. Okay, so what are all these letters mean? What do they mean? What do they represent? And then let's also just quickly write the decay function. So decay is going to be, again, the same thing. A is a function of t, where you have a sub 0 e to the negative kt. The only difference between growth and decay is the sign of k. If k is positive, then it's growing. If k is negative, then it is decaying. And that's all you need to know about it. Okay, so for both of these functions, a0 or a sub 0 is always going to be your initial value. Now, you might be wondering, where is this a sub 0 coming from? If any of you have ever taken a physics class before, or if you're planning on taking a physics class, you'd know that the subscript 0 is always indicative of initial value for anything. Whatever, that value is supposed to represent, it's always going to be your initial value. For example, if you're talking about velocity, in Physics 101, we generally use the letter V for velocity, and initial velocity is generally represented as V sub 0. So whenever you see anything sub 0, just think to yourself, okay, this is the first value. It's the initial value. Okay, T is going to be your time. So T is time, and K is going to be your rate of either growth or decay. Regardless of whatever the case may be, because again, the formulas here, the functions, are essentially identical. The only difference is the sign of k. If k is positive, once again, then you're getting growth. If k is negative, then you're getting decay. So what I want you guys to do is I want you to try to do the classwork assignment. So the classwork assignment is just a little word problem here that involves growth or decay, and see what you guys can figure out. Again, you're going to just be trying to plug into these formulas, and then you'll need a calculator because there's no way that you'll be able to do it. What I want you to do is, if you do try to get, or if you get far enough to where you can get an answer, round to the nearest first, to the nearest digit, to the nearest integer. Okay. All right. So I will give you a couple seconds for the classwork, and we'll see what you get. All right, so the classwork assignment says the following, and I'm not going to write out the whole word problem because it should be right on your classwork assignment. I'm only going to read over it and write out the important details. You buy a fishing boat for $22,000, pretty expensive fishing boat, but so be it. Some people like to fish. You buy a fishing boat for $22,000. Your boat depreciates exponentially annually at 18% of its value. Find the value of the boat after 6 years. So let's break down what we have. We know that when you first buy it, at the very first instance that you purchase it, it is worth $22,000, which tells you it is initially worth $22,000. Remember, what is your initial value? Your initial value is a sub 0, right? So in this word problem, a sub 0 is equal to, oh God, am I running out of room to the right? No, we're okay. A sub 0 is $22,000, or 22,000. Okay, what else do we know? We know the rate that it is depreciating, and depreciating should be indicative that this is decaying, right? It's going down. Depreciates means, the value is lowering and lowering over time. So you know that you're going to be using your decay function. So your decay function is as follows. A is equal to a sub 0 e to the negative kt, right? So we know this to be true. Okay, and now again, we know that k is depreciating annually at 18%, right? So 18%, which when you write this in decimal is 0.18. Okay, and last but not least, you just need to find how long this is happening. So we're figuring out the total value of the boat after 6 years. So your time is 6. And this should make sense that, remember, a, it's not just a, it's a function. It's a of t. This is a function based on time. Regardless, what your initial value is or what your rate of growth or decay is, your function is based on how long it's happening, right? So we know then we want to find out what our function value is when t is equal to 6. So we set this up. So we say, okay, well, a of 6, remember, 6 is your input for your, whenever you're talking about a function, this number here is always indicative of your input, and that's what you're plugging in for t. So a of 6 is $22,000 or 22,000 times e to the negative 0.18. We know it's negative because, again, it's decaying, right? It's depreciating. So negative 0.18 times 6. And we can simplify this a little bit before we plug it into a calculator. So simplifying this down, we get 22,000 e to the negative 1.08. And when you plug this into a calculator, you get 22,000. When you plug this piece into a calculator, you get 22,000 is equal to 0.3396. And again, when you simplify this down and when you round it to the nearest whole number, it is approximately equal to 7471. So what does this tell you? This tells you that after 6 years, only 6 years, the purchase that you made of $22,000 is only now worth $7,471, which tells you that after 6 years, your fishing boat is only worth about a third of what it was originally worth, which, tough break there. But that's really it. All you're doing is you're just plugging into your equation, right? You're just plugging into a sub 0, k, and t. And the hardest part is just figuring out if this is growth or if this is decay. If your numbers should be going down, it's decay, and you make k negative. If your numbers should be going up, if it's, the numbers are rising, then k should be positive. And that's the only difference here. Okay? All right, let's move on here. So that is the end of chapter 4.1. We're going to move on now to chapter 4.2. And in chapter 4.2, we are going to look at essentially the last type of function that we will be discussing, except for trigonometric functions, which will come right at the end of the semester. So the last type of function that we're going to be looking at that's not trigonometry is logarithms. So 4.2 is all about logarithmic functions. Okay, so remember, again, from literally the last lecture and even a little bit of this lecture, that an exponential function is going to be in this form. F of x is equal to a to the x, right? This is just the basic exponential function. Okay, so let's go ahead and quickly replace f of x with the dependent variable. We always know we can go back from function notation to an equation just by switching f of x out with y. So now we have y is equal to a to the x. Okay, so when we have something like 27 is equal to 3 to the x, this is really easy to see upon inspection that your x is equal to 3, right? You can toy around with a couple different numbers if you were trying to solve this to plug into x and see what you get. But after, a couple guess and checks, you can always figure out that x is equal to 3. And so what that means is wow, that was some dyslexia right there. 27 is equal to 3 to the third, right? So x is equal to 3. But when we have something that's not intuitive, how do we figure it out? How do we find the value for x? And what I mean by not intuitive is, say we had something like 5 is equal to 3 to the x. How do we figure out the value of x here? Does x not exist? Is there not a number that makes this true? Well, no, there absolutely is a number that makes this true. It might not be a whole number. It might be fractional. It might be irrational. We don't know yet, but there is absolutely a number that will make this true. But figuring it out right now is really tricky. We don't actually have the tools to do it yet. So trying to figure this out is, we kind of hit a roadblock with it in its current form with exponential functions. So this is where logarithmic functions really come in. And before I explain what a logarithmic function is and why it's so useful, I feel like it's a lot easier for students, for you all to see a logarithmic function in practice, and then we'll go back and figure out what it actually means. Okay, so let's go ahead and erase this, and let's just kind of mess around with the form of logarithmic functions. Okay, so if we have y is equal to a to the x, this is an exponential function. This means the exact same thing. We can go freely from exponential notation, so this is exponential notation, to logarithmic notation. And logarithmic notation is where we have the following. You have log of whatever your base is, so log of whatever your base is of your exponent. So a in this case is your base, right? So we have log with base a. And then this is where it gets tricky. The value that comes right here next to your log is going to be the value that's on the other side of the equation. So it's log base a of y is equal to x. So you can freely go from exponential notation to logarithmic notation, and these mean the exact same thing. It's just that notice how in this case, you're solving for y, right? Essentially, you're plugging in a value for x, and you get some sort of output. The logarithmic notation is really nice when you're trying to figure out the exponent. Notice here how your exponent, x, right? This was originally your exponent. That is now just some value. Logarithmic notation, the way that you can think about it, is you took an exponential function and you're solving now for the exponent. So x is now the piece that we're solving for. Also, another interesting thing to keep in the back of your head before we, actually go back is think about how this looks as far as functional notation. If you were to make this as a function, you replace y because y is your dependent variable, right? Y is very much based on what you plug in for x on the left-hand side, right? If we're talking about exponential notation, y is based on what you plug in for x, because it's a to some x gives you the output y, right? So we can replace y with f of x is equal to a to the x. However, if we come over here, that is no longer the case, right? We have some operation happening to y, and that is going to give us some output x. So when we go from exponential form to logarithmic form, the dependent and independent variables switch. So now we say, oh yeah, x is now our dependent variable, which means we change x to be f of y is equal to log base a and y. So if you're going freely from one to the other, notice how the dependent and independent variables change. Okay. So there is some rigmarole that goes into this. Just as exponential functions have to have a positive base. So remember that for exponential functions, a has to be positive and a cannot be 1. Both this and this are true for both of them. So your base cannot be 1 and your base has to be a positive number. So whatever your a is, if we're talking about the base of your exponent or the base of your logarithm, which I'll circle here, this or this, it has to be a number that's positive and it cannot be 1. Okay. All right. So let's backtrack here. Now that we kind of described the form of logarithms, let's go back and talk about what they mean. And to really understand what they mean, what we should do is we should do a refresher of inverse functions. Inverse functions we talked about back, we touched on it from chapter 2.9. I kind of smushed that in with 2.8. And that was when we were talking about composition of functions. So if you don't remember, inverse functions, go back to composition of functions and you'll see it in that lecture. So what is an inverse function? So again, you can think about an inverse function as a function that undoes what the original function does, right? So let's say we have, again, we'll do a quick example, f of x is equal to x plus 2 over 3. And I want you to find, find f inverse of x. Remember, inverse notation is where you have that -1 attached to your function. So I want you guys to find the inverse, and this is actually your second classwork assignment. So go ahead, see if you guys remember how to do this, and if you don't, well, then just stick around. We'll go through it together. But this is a good refresher for inverse functions because we didn't spend a whole lot of time on this. Okay. So hopefully you gave it a shot and it wasn't that bad, but if you don't remember, that's okay. We're going to go through it together. So the process to find the inverse is you always start with your original. So starting with your original, again, we have f of x is equal to x plus 2 divided by 3. Now what we do is we switch it out of function notation. We put it into an actual equation, right? We have two variables, y and x. So we have x plus 2 over 3 is equal to y. The next thing that you do, and this is the actual piece to figure out how you find the inverse, is you take the positions of your two variables and you just switch them. So wherever you have one variable, you switch its place with the other one. So we have a y on the left, we're now going to make it x, and we have an x on the right, we're now going to make that y. So we have x is equal to y plus 2 divided by 3. And now the last thing that you do is you solve for the original variable that you had on, that was isolated before. So y was isolated before. We're now going to solve for y all over again. Okay, so isolating for y, we're going to multiply both sides by 3. So we get 3x is equal to y plus 2. And now to isolate for y, we just subtract 2 on both sides. And I'm just going to keep y on the left-hand side. So I'm going to have y is equal to 3x minus 2. Again, all I did was I subtracted 2 from both sides, but I swapped the sides so that way y was on the left because I had y on the left over here. And now what this tells me is my inverse function is 3x minus 2. And if you guys don't remember how to verify that this actually is, in fact, your inverse function, well, the way that you do it is you compose the two functions together, and you should just get your variable x back. You should just get a singular 1x back. So we're going to compose the two together just to really make sure that this is, in fact, our inverse function. So we have our inverse function f composed with f. And what does that mean? And remember, you could do this in either order, right? You can either have your inverse f composed with f, or you can have f composed with your inverse f. Order does matter, but in this case, you should get the same answer either way. So we get an outside function and an inside function, right? That's what composition of functions means. So my outside function, as it's written, is I have my inverse function of f of x. But we know what f of x is, right? F of x was given to us, and that's this piece right here, x plus 2 over 3. So that means I now have my inverse of x plus 2 divided by 3, and this piece underlined in red is my new input for wherever there was an x in my inverse function. So we look at my inverse function here and we say, okay, wherever there's an x, I'm plugging in that fraction. So I have an x right here, so I'm going to be plugging in my entire fraction where there was an x. So we now have 3 times, remember this, it's starting with the 3, so I have 3 times this entire fraction, x plus 2 divided by 3 minus 2. Well, what happens here? We have a multiplication of 3 and a division of 3, right? So we can go ahead and cancel these out. And so we're just left with x plus 2 minus 2, and positive 2, negative 2 are going to cross out. We are just left with x. And we have now verified that indeed this f, inverse is in fact the inverse of f. So the function f negative 1 or f to the negative 1 is the inverse of f. So that's how we verify it. Okay, so why did we go through this, the whole idea of inverse functions again? Well, the entire idea of a logarithm is that a logarithm is supposed to be the inverse of an exponential function. That is the entire point of this. So in an exponential function, you're essentially plugging in some value for your exponent and you get some output, right? The idea of inversing that procedure is you have some value plugging into a logarithm and you get some exponent back, right? The value that you get back was the exponent of the exponential function. So if we had, for example, if we had just f of x is equal to a to the x, and again, we know we can switch this to be our equation notation, so y is equal to a to the x. Well, when you find the inverse is where you swap the positions of x and y, right? So the inverse is where you have x and then a to the y, right? So the new equation reads as y is the exponent on base a that gives you x. And the way that we represent this is with a logarithm. So the way that we represent this piece, is with y is equal to log base a of x, which means f, our inverse, again, when we swap that y with our function notation, our inverse f is equal to log base a of x. And you might be wondering, well, wait, didn't we just say that you could freely go from exponential notation to a logarithmic notation? And you can. The difference here is that what we're doing is we're finding the inverse of specifically this piece right here. Notice how this and this are equivalent, but this and the piece in red are not equivalent. The piece circled in black is the inverse of the piece circled in red. Okay, so the two pieces circled in black are the inverse of the piece circled in red. And that's what logarithms are really supposed to do. Logarithms are supposed to be the inverse of exponential functions. So if you didn't really follow everything I just said, that's totally okay. Feel free to come talk to me privately. I'd be happy to go through it a little bit slower. I just, need to, for the essence of time here, I need to make sure that I get through as much as I can. So I'm just going to leave it at this. And then we'll move on to the, logarithms to exponential forms and the properties of logs for the rest of this video. So logarithms to exponential forms. Again, we have, and I'm just going to write this one more time, as long as, and you just have these three properties here, as long as x is greater than 0, a is greater than 0, and a is not equal to 1, then these are equivalent. And for the record, if you're wondering on, why the y is here, well, the y being with the logarithm means that these two pieces are equivalent. If, however, you wrote it like this, which I'm going to write in red, then this is the inverse of that. Okay, the entire idea, the way that you can remember how, which one is the inverse and which one is the equivalent function or the equivalent equation is the inverse is always going to have this piece looking identical to that piece, where, again, your y is going to be off by itself. Okay, so your inverse, it has it matching, and the piece that is equivalent, which is the black, the piece that's written in black here, has the variables flipped. So y and x, notice how that's different than x was with a and y was by itself. Now y is with a and x is by itself. And that's how you know that the logarithmic form and the exponential form are equivalent. Okay? Okay, so let's actually do some math here, and we'll try to figure out what's going on. So what I want to do is I want to rewrite the following exponential equations to logarithmic form. So let's say we're starting with 2 to the 10 is equal to 1024. Okay, so this is currently in an exponential form, right? We have some base, so I'm just going to say, I'll just keep it as a. We have some base, a. It's raised to some exponent, and when we raise the base to some exponent, we get some output, right? This is exponential form. So what I'm going to do is I'm going to plug this into logarithmic form now. Logarithmic form, where it's still equivalent, is log of the same base. I keep the base the same, right? The base of the log is still the same base that had the exponent attached to it. So log base a on my value y, so on y is equal to the exponent x. So when I'm plugging this in, 2 is my a, right? So I have log base 2 of y, which is my value, so of 1024, gives me the output, or gives me the exponent of 10. So this is logarithmic form of the exponential notation. These two circled pieces are equivalent. Okay. Okay, so now let's go through and do another one together. So the next one is if I have 9 to the negative 1/2 equal to 1/3. And for the record, if this doesn't make sense, remember what 9 to the negative 1/2 means, right? If we're going to go through this together, just to really verify that this is in fact true, 9 to the negative 1/2, you deal with the negative sign first. That means 1/9 to the 1/2 power. And when you deal with this, you just apply that 1/2 power. Actually, that's not technically accurate. I apologize. It's been a really long day, guys. I'm so sorry. So the power stays with the 9, right? This power was attributed to the 9. So you bring that 1/2 power to the 9 now, and 1/2 power means square root of 9, right? And the square root of 9 is just 3, so you get 1/3. So we know that this is actually true. 9 to the negative 1/2 power is in fact 1/3. So once again, I want to convert this to logarithmic form. It's an exponential form. How do I know this? I have some base a raised to some exponent equaling, give me, some output y. So logarithmic form is where I have log of the same base on that value y, giving me the exponent. So that means I have log of base 9, right? 9 is my base, 9 is my a. Y is the value that in the exponential form that I got as an output, right? So y is going to be 1/3 is equal to my exponent. So my exponent is negative 1/2. So negative 1/2. And again, this piece here is entirely equivalent to that piece here. This is the exponential form, and this is the logarithmic form. Okay, let's do one more together. One more here. So the last one that we'll do is 10 cubed is equal to 1,000. Okay. So, and hopefully you guys can all eyeball this and understand this is true, right? 10 times 10 is 100, times 10 is 1,000. So anyway, we know that this is in exponential form, right? We have a base, we have an exponent, and we're getting some output, right? So logarithmic form, we keep the base the same, it's on that value, and we get the exponent back as a return, right? So our base, log base 10, our value is 1,000, and our output is the exponent. Our output is the value that, makes this piece true. So logarithmic form is what I just circled, and what I just circled here is the exponential form. Okay, so let's now go and do some evaluations of logarithms. So what I'm going to present here is I'm going to present logarithmic form, and we're going to figure out what this actually comes out to be. So let's say we started with log base 9 of 1/3. Okay, what does this mean? So whenever you're given a logarithm and it says evaluate it, your first step, always, your first step is the same. You set it equal to some variable. You don't know what this value is, so it's equal to some unknown. You set it equal to a variable. Okay, so remember how we go freely from logarithmic form to exponential form. Logarithmic form, this is your base, so that is your a, right? So a, in this case, is equal to 9. Your y, your value is the piece that is attached to the logarithm, right? So your y is 1/3, and your exponent, x, well, x is just equal to x, right? We don't know what the exponent is yet, so we just say, okay, x is equal to x. And now what we're going to do is we're going to convert our logarithmic form to exponential form. So remember, exponential form is your base to your exponent is equal to some value, right? Well, you know what your base is. Your base is 9. You don't know what your exponent is yet, right? So your exponent, you just write x, that's your unknown piece, and it's equal to some value, but we know that value is 1/3, right? Okay. Whenever you're given something in this form, evaluate the logarithm, you're always trying to play a game. The game that you're playing is you want to make the number that is the base of your exponent and the number that's on the other side have the same value. So the reason that you want to do that is because if you have the same values, you can do something really cool with the exponents. So if you had, really quickly, for example, if you had 2 to the x is equal to 2, what you can do is you can set the exponents in their own equation. So what's the hiding exponent here for the 2 that's on the right? Well, the hiding exponent is a 1, right? So what you can do is you can say, okay, well, if I have the same base here as I do here, I can take my exponents and set them in their own equation. So I can say x is equal to 1, And, well, you would normally solve for x, but in this case, it's really basic, right? You're done, right? There's nothing that you have to do, so x is equal to 1. Basically, you're looking for the exponent that makes this equation true. So, yeah, 2 to the 1 is equal to 2 to the 1, and that's 100% accurate. If we made this a little bit harder, if we add 2 to the x is equal to, let's say, 4, for example, well, what we have to do is we have to change the 4 to be in the same base as 2, or we have to change 2 to be the same base as 4. Either way, however you want to approach it, you just have to make sure that the bases are the same, and then you set the, you set these pieces here equal to each other. So I'm going to manipulate the 4 here without changing the value. I'm just going to use exponent properties, and you have to be really versed with your exponent properties to be able to get through this, okay? So 2 to the x is equal to 4. Well, what do I know about 4? I know 4 is 2 squared, right? So I can say, okay, well, 2 to the x is equal to 2 squared. And then what I can do is, again, I have the same base. I have the same base there. I can just set a new equation where I set my exponents equal to each other. So I have x is equal to 2. And once again, this is done, right? You now solved x is equal to 2 because there's no solving that has to go on. So what you just found is the exponent that makes this equation true. And to show you that you can do it the other way, you can manipulate the left-hand side. Well, manipulating the left-hand side, 2 is the same thing. If we're trying to make 2 to be 4, well, how do we get 2 to be 4? 2 is the same thing as 4 to the 1/2 power, right? Because again, 4 to the 1/2 power is the square root of 4, which gives you 2. So, okay, what I'm going to do is I'm going to say 2 is really 4 to the 1/2, and we keep that x on the outside, and this is equal to 4, right? But what do we know about a number raised to an exponent raised to another exponent? Well, this is the same thing as you multiplying the exponents together, right? M times n. So what I'm going to do is I'm just going to multiply 1/2 and x together. So we get, oh goodness, my tablet's lagging. So we're just going to get 4 to the 1/2 x is equal to 4. And now we have the same base here. We have the same base here. So I can set my exponents to be equal to each other. What's the hiding exponent for 4 on the right? Well, it's just a 1, right? So I have 1/2 x is equal to 1. And solving for x, we get x is equal to 2 by multiplying 2 on both sides. So notice we get the same answer either way, regardless which side you manipulate. And you could actually end up manipulating both sides to make life easier for yourself if that's something that would happen. Okay, so that's the game that you're playing. So let's go back here now. We know that we just converted our logarithm to exponential form, right? We started with this logarithm, and now it's in exponential form. So what I want to do is I want to convert one of the sides so that way I can start getting the same bases, right? Right now I have a 9, and right now I have a 1/3. I want to get those bases to match. So the first thing that I'm going to do is I don't like fractions. I think fractions are really annoying. So I'm going to keep this as 9 to the x for right now, and we'll come back to it if we need to. And then I'm going to make 1/3 3 to the -1. We know our exponent property of negatives, right? If we have a negative in our exponent, that means we flipped it on its head, right? 1/3 is the same thing as 3 to the -1st power. So, okay, sure. We now have a 9 here, and we now have a 3 here. And we're getting closer, right? So what we want to do is we want to say, okay, well, if I have a 3, how do I make 9 look like a 3? Well, 9 is the same thing as 3 squared, right? So, okay, we have 3 squared, to the x, 3 to the -1. And again, by our exponent properties, we know we just multiply the exponents together. So this is 3 to the 2x, 3 to the -1. And solving here for x, we set, because we have the same bases, we set the exponents equal to each other. So 2x is equal to -1. And now solving for x, we get x is equal to -1/2. So what does this say? This tells us that when we were solving for x, we got x is equal to -1/2. So back here for this logarithmic form, when we had log base 9 of 1/3, this is equal to -1/2. and that's your final answer. Okay, I know I kind of went about that a little backwards. We took a little detour with, showing a couple other examples, but the idea is what you're doing is you have it in logarithmic form, you're going to convert it to exponential form, and then using exponent properties, you're going to manipulate the bases to be the same. Once you have the same bases, you can then set the exponents equal to each other, and you get a result where you've solved for that exponent. And solving for the exponent means you have then solved the logarithm. Okay, so we're going to do another one together here. Let's say we have log, let's say we have log with base of 1/2 on value 32, and I want you to evaluate this. So to evaluate it, once again, your idea is the same. You're going to set it equal to a variable. You don't know what this is equal to, so you set it equal to x. Okay. Sure. Now what you're going to do is, again, you convert this from logarithmic form to exponential form. So logarithmic form is where you have log of base a on, some value y is equal to x. And exponential form is where you have the same base to your exponent x. Remember, this is indicative of your exponent. So to your exponent gives you that value y. So we have 1/2 to the x. We don't know what x is, but we know our base is 1/2, right? A is 1/2. So our base is 1/2 to the x, and we know our value y is 32. So we have 1/2 x is equal to 32. So once again, our game here is we have to manipulate the bases so that way we can get the same base on both sides. And once we have the same base on both sides, we set the exponents equal to each other. So setting the exponents equal to each other will give you the answer for x, which in turn gives you the answer to the logarithm. So to do this, we look at 32 and we also look at 1/2. Once again, I'm not a fan of fractions. So what I'm going to do is I'm going to convert my 1/2 to be 2 to the -1 to the x is equal to 32. And I think by now we're all used to that exponent rule, where if I have a base raised to an exponent raised to a second exponent, I can just multiply them. So instead of 2 to the -1 to the x, I'm just going to write 2 to the -x is equal to 32. Okay, we're getting closer. What is 32? You ask yourself, okay, well, how do I make 32 look like a 2? How is this going to work out? Well, 32 is even, right? So your first step is you can say, okay, well, if I take 2 out of 32, I get 16. If I take 2 out of 16, that's still even. We get 8. 8 is still even. 4 is still even. And then you just end up with 2, right? 32 is actually a power of 2. And when you go through it enough times, you can realize, oh, yeah, 32 is really just 2 to the 5th. And now you have the same base, right? You have 2 here, 2 on the right. And since you have the same base, you can now set your exponents equal to each other. So what I'm going to do is I'm going to set -x is equal to 5. And solving for x, that means multiply or divide both sides by -1. So we get x is equal to -5, which then we come back to our logarithm and we can then say, okay, log of 1/2, log of base 1/2 on 32 gives me -5. And that's all there is. Okay, the idea is, again, you're just taking your bases and manipulating them with exponent rules, so that way you get the same base and you set your exponents equal to each other. Okay, and you can obviously manipulate the left side to look like 32 if you wanted to, or you can manipulate 32 to become a fraction, right? 32, if we wanted to, we can say, okay, well, 32, if we wanted to make it a fraction, it's the same thing as 1 over 32 to the -1, right? That negative exponent just flips 32. Instead of it being 32 over 1, it's now 1 over 32. And now when you have a fraction, okay, you can just, do some things there. But that wasn't the step that I took. I took making 1/2 into an integer. So, feel free to go about it however makes sense to you. Okay? All right. So that, I think, is the last example of that. It is. Okay, so there is a couple remarks that I want to note here. The first is that process that I just described will fail for 2 numbers. And the 2 times it'll fail is when you have 0 and 1. And remember what your rules are, right? Your base can't be 0 and your base can't be 1, right? Your base has to be a positive number and your base has to be a positive number that isn't 1. So when you think about why it'll fail, well, think about it. If your base is 1, so if we add 1, and say we add, when we converted a logarithm, we got 1 to the x is equal to 5, for example, right? I'm sorry, 1 to the x is equal to 1. Let's say we had this. What is the power to the, that's hiding on the right-hand 1? Well, the power is 1, right? We always assume that power is 1. So you could say, oh, yeah, well, sure. Now we just set the exponents equal to each other. So x is equal to 1, and I'm done. The problem here, though, is that x could actually be any number, right? If we plug in 2, this equation is still true. 1 squared is the same thing as 1 to the first. If you plug in -4, this is still true. 1 to the -4th is equal to 1 to the first power. So just because you have a first power over here does not necessarily mean x is also 1. Okay, so because x can be any number, we know it'll fail for your base of 1. And for your base of 0, same idea, right? If you add 0 over here, well, again, if you are talking about the number that's here, we know that for any number, for any exponent that's not 0, 0 to any exponent is always going to give you 0, right? So 0 squared gives you 0, 0 cubed gives you 0. So just because that's 0 to the first power doesn't necessarily mean x is 1. X could be 7. 0 to the 7th is also equal to 0 to the first power. So we run into this situation where you know it's going to fail for 0 and 1, and that's one of the reasons why we exclude it from, from doing this. So 0 and 1 will not work. And that's, again, when you're talking about your logarithmic rules, your base can't be 0, can't be a negative number, and also it cannot be 1. Okay, the second remark here is because a logarithm is the inverse function of an exponential function, the domains and the ranges are going to switch. So for exponential functions, we already talked about the domain is going to be from 0. The domain is going to be all real numbers, right? So it's going to be from -infinity to infinity, and the range is going to be from 0 to infinity. Well, for a logarithm, they switch. So for a logarithm, the domain is going to be from 0 to infinity, and the range is going to be all real numbers. Okay, so that's just a rule that you should know, that because logarithms are the inverse of exponential functions, the domains and ranges switch. Okay, I've been talking for a little over an hour. I just want to move on real quick to the properties of logarithms, and then we'll close this out for today. Okay, so properties of logarithms. There are 4 that you should know. These are 4 properties of logarithms that are very imperative for you understanding logarithms and how to evaluate them. So I'm going to write them out. So 1, 2, 3, and 4. The first rule is if you have a log to some base a, on that same value of a, it's always going to equal 1, regardless what a is. A could be 7, a could be 24. If you have log of base 24 on 24, your value is always going to be 1, okay? Second rule is if you have log of any base and your value is 1, your output is going to be 0 every time. Your third rule here is that if you have log of a base a, and it's on a to some other exponent, so, a to the x, your output is always going to be x. And if you have, and this is, I'm going to put this in parentheses here because this has to be true, if x is greater than 0, then a to log base a x is equal to x. Now what I'm going to do here is I'm going to go through some really quick proofs, but for 1 and 2, these should be really simple when you just convert them to exponential. So for 1 and 2, let's convert them to exponential. So 1 says if I have log on base a on that same value a, I should get a 1, right? Well, think about it. If I convert it to exponential, I have my base, which is a, so I have a, and then this is my exponent, right? So I have a to the 1 is equal to a, And yeah, a to the first power is in fact a, right? A is equal to a. Yeah, this should work out regardless of what, my number is. So yeah, the first rule kind of just falls out just by switching it to exponential form. The second rule also does the same thing when you switch it to exponential form. You have log with base a of 1 should give you an output 0. Switch it to exponential form. Let's see what it looks like. So we have base a. This is going to be my exponent, right? 0 is always, the right-hand side is always my exponent in logarithmic form. So, or, well, not the right-hand side. I should say the side that doesn't have the logarithm is always the exponent. So 0 is my exponent, is equal to 1. And yeah, this is one of our exponent rules going way, way back several lectures ago, where we talked about, yeah, any number to the 0 power gives you 1. The only exception is when a is equal to 0, but we know by properties of logarithms, your base can't be 0, so you don't need to worry about that. So any number to the 0 power equals 1. So yeah, this works out. So your second rule just falls out by switching it to exponential form. Your third and fourth rules, these are the only ones that are a little bit tricky. So I'm actually want to go through a little bit of a proof here and show you guys why these are the case. If you don't understand the proofs, again, it's okay. Just understand how they work. That's more important for the purpose of this class than understanding the proofs, although I really encourage you to understand the proofs as best as you can. Okay, so for proving number 3 here, we have this piece, right? So log base a of a to the x is going to give you x. Okay, so to start this, we have to understand inverse functions. So remember that when you compose an inverse function with its original, you always get your variable x back, right? You always get your input variable as a return. So, okay, well, we know that let's let f of x equal an exponential function. So let f of x equal a to the x. And then by the definition of logarithms, we know that a logarithm is the inverse of an exponential function, right? So then we know then that our inverse function should be log with base a on that variable. Remember, I told you guys that when we talked about inverses of exponential, that you know that this is always going to be the inverse of your exponential function if this piece matches this piece right here. So yeah, this is the inverse function. So okay, we have f of x and f inverse of x. So how do we get this right here? Well, let's compose them together. Let's see what happens. We know then by default that x should fall out, right? If we compose these two together. But what is f of x? And also, what is the inverse of x? Well, f of x by our let statement is this piece right here, right? F of x is a to the x. So we can replace this with, okay, well, this is our inverse function of a to the x. But what is our inverse function? Well, our inverse function is the logarithm. So we know that we can do even one better. We get our logarithm of base a, but wherever there's an x, we're plugging in this new input, right? That is the whole idea of composing your functions together. So, okay, well, we have our log of base a, and there used to be an x right here, but instead of an x, we're plugging in that new input, which was f of x, so a to the x. And we know our answer should still come out to be x. So the entire idea of number 3 here is that you have an inverse of the same function, right? You have an inverse of f being composed with f. So of course you should always get just your input variable back. Okay, so it doesn't matter what a is for number 3. If a, as long as this matches this, you're always just going to get your exponent back. Okay, so that's number 3 there. Number 4 is actually going to be very, very, very similar. So the idea behind number 4 is just you're switching which one is your function and which one is your inverse function. So for number 4, you're going to let your main function be the logarithm. So you have log base a of x. And then if that's the case, again, by definition of inverse and by definition of exponential and logarithm forms, you know then that the inverse function of f is going to be the exponential, right? So it's going to be a to the x. And what you're doing is, okay, you're starting the same way. You know that when you compose them, you should get x back, right? X is equal to the composition of any, an inverse function and its regular function put together. So you have this being the case, right? And now that this is the case, well, you're just plugging in and seeing what happens, right? F of x is going to be your logarithm. So you have, your inverse of log a to the x. And the inverse function, well, this is now your input into that inverse function, right? So wherever there was an x, you're plugging in this entire thing for x. So that means, okay, well, we have a to the, this entire piece here, log base a to the x, and you should just get x back as a return. Okay, so the entire idea behind number 3 and number 4 is that number 3 and 4, you're really just composing your two functions together. You're composing a logarithm with an exponential function, and for number 4, you're composing an exponential function with a logarithm. And when you do that, you should always get x back either way, because you're composing an inverse function with the original function. The whole reason that you have this here, number 4 only works when x is greater than 0, is because you have to remember that when we compose functions together, we care about the domains, right? So we care about the domain of the inner function and also the domain of the composition. So for number 3, the domain of the inner function was just the domain of an exponential. But for number 4, notice how the domain of the inner function is the domain of a logarithm. And we already talked about how, the domain of a logarithm is from 0 to infinity. So we can only say number 4 works when x is positive. I know that was a lot of talking, and maybe that didn't make a whole lot of sense, but maybe watch this again and see if it makes more sense on the second playthrough. And if not, come talk to me, because I'll be more than happy to walk you through it. Okay, so I just want to end this video with one last classwork assignment. So the last classwork assignment is I want you to evaluate the following. So evaluate log base 3 of 3 to the 5th. And then I also want you to evaluate, now notice the change in parentheses, log base 3 of 3 to the 5th. Okay? So try to use the rules that we just talked about above, the properties above, the first 4, and see if you can figure this out. Okay, so for the first one, let's do one at a time. Let's do this guy right here. So we're going to do log base 3 on 3 to the 5th. Okay. So your idea is what you want to do is you want to set this equal to some variable, right? I told you whenever you're evaluating a logarithm, set it equal to a variable because you don't actually know what that number is, right? So, okay, set it equal to a variable. Okay, now what I want to do is I want to convert it to exponential form. So, converting it to exponential form means, okay, I have b to the x, or well, a to the x. So a to the x is equal to y. My base is 3, right? So my base is 3, and that means I have 3 over here. X is my exponent. So I don't know what x is, but I have my exponent. And then y is this piece that I have right here, so 3 to the 5th. So 3 to the 5th. Oh, and yeah, look, this falls out. We know, hey, we have the same base here, we have the same base here, which means the exponents should be equal as well. So x is equal to 5. So you have now shown that log base 3 on 3 to the 5th is equal to 5. So that's if you did all the work. But you can actually just use the properties to just get that same exact answer. What was our third rule? Our third rule that we just talked about is log of base a on a to the x is always going to give you x, right? So we just had log base 3 on 3 to the 5th. Well, notice how it should just give you x, right? So it should just be 5. And that's just falling out of your third property rule. Okay, but of course you can solve it by doing the third way. Okay, so the other one is now we have log base 3 on 3 to the 5th. Now notice that the exponent is applied to the entire logarithm. Before, the exponent was only being applied to the 3, right? So that's not the case anymore. So what we have to do is we have to figure out this value first. And once we figure out that value, then okay, we can then take care of the exponent, right? So what I'm going to do is I'm going to set log base 3 of 3 equal to x. But this is one of our rules, right? If we have the same base matching, then it should always come out to be 1. This is our second rule, right? Or, I'm sorry, our first rule. If we have log of some base on some number, as long as that base and that number match, it should always be 1. So I know that x is equal to 1. And then all I have to do is, well, I have, again, log base 3 on 3 to the 5th. But I know that this is now, this entire piece on the inside is just 1. So it's really just 1 to the 5th. And 1 to the 5th is still just 1. So this is your final answer here. All right, guys, so that's it for today. I went a little bit longer than I wanted to, but it's not terrible. There's not a whole lot left in this chapter. In the next chapter, we will be looking at more about logarithms. So logarithms will go away probably after the next lecture. All right, guys, try the homework. Get back to me if you have any questions, and enjoy the rest of your night. I will talk to you next time. Have a good one.